Where did radians come from? Why do we use the word radians? Why do we use 2 pi? Why do the radians seem to vanish when we're working with our equations? These are the questions I always hear from students, and I witnessed it. This video is dedicated to a couple high schools I visited recently, East Lake High School and Shorecrest High School, where students were grappling with these questions. So I wanted to give a little history on where radians come from, tell students that you're not the first people to ask these questions, and there's still people grappling with these questions today. There's still argument about the units going on, and I'll give some of that history at the end. But I do want to say a little bit about why we do what we do. Ultimately, for us in our courses, these formulas, oops, I changed a color there, that was unintentional. These formulas are what it's all about. These are incredibly valuable if we're going to study circular motion in any way. If we're going to study how a bike works, if we're going to study rotation. I've made videos about how to model the teacups at the Disneyland resort. I've made other models using circular motion. All of those require that I had an understanding of these models. Okay, so Harry's going to help us here. I've got him here in this picture. I'm going to show some visuals in a second, and then we'll finish with some history. So we've got a circle, and we would like to measure how things move and do some motion. A little bit I'll show Harry going around here, pointing at this point. That's our mascot here at the University of Washington. Thank you for helping us out. I'll talk about that star in the middle, but let's do a little bit first. And I've got a whole bunch of things I can change here. But let's put you back at the beginning, Harry, and let's simplify things a little bit. And let's just talk about how we're going to first cut up the circle. Now, one way to cut up the circle is just say 1 revolution or 1 rotation counts as 1. And that's a really natural way to do it. I mean, when I was making my visuals of the Disneyland teacups, I found a video of my family writing it, and I was just able to see things like, oh, it completes 1 revolution every 30 seconds. And so then I could say 1 revolution every 30 seconds. And that was like where I started doing my little problem. So revolutions is typically easy to see and measure. If you're watching the Great Wheel in Seattle, you could sit there and you could look at your stopwatch and you could see how long it takes to do 1 revolution. But revolution is sort of hard to work with because if you're only going to go a little bit of a revolution, you're going to be using all these decimals and it doesn't come up very nice in our formulas. It doesn't mean you couldn't use it. So somebody at some point said, let's use some other way of cutting up a pie. And what I have here is some cuts. So there's cutting up a pie into 4 pieces. Actually, it's 8 pieces because you can't see that little subdivision. So let me increase. So there's a whole bunch more pieces. So what would make sense? To me, it would make sense to cut it up into like 10 pieces or 100 pieces because everything else we do is like that. I was looking up some of the history, and you probably already know this because we're used to it, but the standard way is to cut it up into 360 slices. You can't even see the slices. So at first glance, that's kind of nonsense. So I pulled up something. So a little bit of history here. This is from... we're going to make this vanish for a second. History Today. I just found a random site online that talked about this. And there's not precision known about where the 360 comes from. The governing hypothesis is that, and now you can read and find this, but the Babylonians used a base, I forget what base they used. But they used something based off of days of the year, and 360 is almost 365, and so it just became a number that was prevalent in these calculations. Even today, sometimes in banks, they use 360 instead of 365 for certain calculations because it's more divisible by other things. So it's really pretty arbitrary why we use 360. Okay, so sometimes students are complaining about the radian measure, but maybe you should be complaining about degrees. And then we just break things up. We say, okay, if we're calling that 360 degrees, even in Euclid's Elements, Euclid's Elements was written It was the only math book. It was the second most published book of all time behind the Bible. So it was a very important geometry book for a long time. They didn't use degrees or radians. They talked about right angles, but there's no mention of, and they talked about angles, but there was no mention of a measurement. I hadn't seen that until I was looking at that history. Okay, so too much history. What we do is we use a conversion. We say, well, what do we want revolution to be the same as? And I always think of conversion in this way. Well, let's call it 360 degrees. And sorry, I'll get to the visuals here in a second. Okay, so then I could convert if I was watching, whatever, I was watching the Disneyland teacups, I could convert it to how many degrees we complete in a second. Now, the bad part about that is most of the time when you're doing circular motion, you'd like to measure what's happening around the edge of a circle. So I'll try to look at this here. If you look at, let's make this a little bit more reasonable. And let's do this. I've drawn one, I'm going to make this really small so you can see it. I've drawn one wedge. So here's if you did 20 subdivisions, and there is one wedge kind of labeled with these purple. And I've drawn these two red stars. So I'm going to go for a little walk here on those red stars and see what happens. So if I walk out, one could ask, how far does that compare, that distance I just walked, to the distance between those two along the edge? Along the edge, that's called the arc of the circle. It turns out there's not a nice relationship between them. It involves messy numbers. So a natural thing to ask would be, how could we make the arc length as nice as possible? And it turns out it's not very nice when you're doing 20 subdivisions. It's not very nice when you're doing 10 subdivisions. And it's really terrible when you're doing 360 subdivisions. They're almost touching. You can hardly see the difference between them. Okay. So that leads to fairly complicated, somewhat messy formulas with kind of not nice constants. All right. So let's get rid of that and rethink our system. And you can actually figure out the formula. The formula for the arc length I have written up here if you're in degrees. It says figure out what your angle is, multiply by 180, divide by pi, multiply times the radius, and that will tell you the length around the edge that I was just talking about. So someone came along and said, could we make this nicer? And the history was showing, I think it was the early 1900s when it actually got a name. That doesn't mean it hadn't been used. Euler was using those formulas, S equals theta r and V equals omega r, in his writings. And I believe I read that it's what really made it popular. So he was but he didn't use the word radians. He just used the formulas as an understanding. Okay, so now here's what we're going to do. What if instead we say that one revolution is 2 pi radians? What does that tell us? Well, there's a reason it's nice, because it comes up in the circumference. So if one revolution is the same as going all the way around, then you can think about what distance that corresponds to. It corresponds to 2 pi times the radius. Watch my previous videos on that. It's the diameter times the radius. And let's just give it a unit, feet. That many feet. So one revolution would be that many feet. In all of these formulas, what you end up doing is dividing by how many slices. So you could divide that up into, so many slices. How many do we want to divide it up into? Well, it'd be nice if there was a direct connection between the angle and the length. Okay, so that gets us thinking. How can we have a direct connection between the angle and the length? Well, what if we divide it up in a certain way so that there is a connection? Okay, I'm just letting us think about it before I give away the punchline. Okay, so now I'm going to reconsider the following little picture, and we're going to send Harry on his way. And when he gets to 1 radius, so we're going to keep track of his walking, and I want the distance around the edge there to be the same as the radius. And let's make the radius something we recognize. We're going to make the radius 3. So Harry has walked 3. So let's do that again so you can see it. Harry has walked here, and now he is at 3. So I figured it out. I was like, I want that to be 3 along the edge. An interesting thing about that is you get this wedge where all the way around it is 3 and 3 and 3, because the radius is 3 and the length along the edge is 3. Let me show you. That's 3, that's 3, that's 3, that's 3, that's 3, that's 3. This is what I would call a radian wedge. And we start to realize it really would be nice if we had this direct connection between the angle. So somebody came along and said, let's call that one radius. We've traveled around the circle 1 radius. And that's where the name comes from. 1 radian is that angle right there you're looking at. Okay, so what happens if we keep going? So that's 1 radius. You can continue to look at Wedge Park, but let's send Harry along a little further. I'm going to stop that for a second. Let's send Harry along. So that was 1 radius. Let's go to 2 radius. That's 2 radius. And I'm going to show you a little more. Oops, I didn't mean to show all of them. Apologies. All best laid plans. Okay, so here we go. There was 1 radius. There was 2. So that length along the edge is the radius. Let's keep going. Let's go to 3 radiuses, which is going to be right there. Come on, Harry, get moving. Okay, we're going to 3 radiuses. There we go. That's 3. So each one of those has length 3. We didn't quite make it halfway. Darn it. Let's go to 4 radiuses. So again, those are not hitting on nice values, but it provides a direct connection. There's 4. And then we'll go to 5, and then we'll go to 6. And this is 6 radians, 6 radiuses, I should say. 6 radiuses that we've traveled around this. There was 5, there was 6, and we're a little short. And that little gap is that, that part we were talking about when we were talking about what pi is. We would say it's 3 diameters or 6 radiuses plus a little bit. And that's it. We would like to call it 2 pi all the way around. And then it makes our formulas really nice as we go around. It unfortunately makes it so we have this messy number, but that's what we get. Okay, so a few little comments before I say more here. So what we get is linear speed is defined to be distance over time. The distance Harry has traveled is his arc length. It's that thing we're calling S. It's how far he traveled around the circle, and let's just label this with T. The arc length is going to be whatever our measurement is, and we have decided that when theta is 1, the distance is r, and when theta is 2, the distance is 2r. That's the clever observation. That's the thing that makes this all go. So when theta is 1, we want S to be R. When theta is 2, we want S to be 2R. That's that radian wedge I'm talking about. We want S to be 3R. And so on and so forth. I was writing this and realized you can't see it. Let me move it over. So when theta is 1, we want S to be 1, just to be R. When theta is 2, we want S to be 2R, and so on. So in general, we'd like to define an angle measure so that when you're given a theta, we get S is theta R. And also that means when we go all the way around, it's going to be 2 pi R. If we could figure out such a measurement, then this would be 2 pi R. That would be that distance, which would be just theta R. Sorry, 2 pi R. It would be theta R in general over T. And then that brings everything together. Harry, sorry, I'll make it smaller for a second. That brings everything together, because theta over t, that's what this is. And distance over t, that's what this is. And everything will line up perfectly if we have this relationship. So that will be omega. And then you get this really valuable formula. Phi is equal to omega r. But only if you say that 2 pi is the same as one rotation, revolution all the way around. So that was used for, it appears, centuries, and then in the early 1900s, someone published a book and said, we should call that radians. I think they were thinking, hey, it's how many radiuses we go around. So that's the name. That's where it comes from. But let's say a couple more little things and then show some history. So lastly, about the belt and wheel piece. Here's where this is so valuable. I mean, if you have two things that are connected by a spoke, we say. So I usually, when I do this in class, I might call this, let's call the pedal A. That's the thing we're pedaling and moving. It's connected by a chain to the back of your wheel. Let's call that circle B and circle C. I often have students, and I saw some students doing this in the high schools I visited, making a little table. And I think I'm a proponent of this method. So you can write it, and I'll think about maybe the best way, but let's just write V and omega and R and lay these all out. Lovely. And then we could say, well, I know how fast I can pedal. I can pedal in a way that completes, I don't know, let's say 5 revolutions a second. I'm pedaling really fast, 5 revolutions a second. I don't know if that's reasonable or not, but unfortunately revolutions is not in radians, and I want to use this tool. So you often have this moment where you say, well, if I want to do 5 revolutions per minute, and I didn't think about these numbers ahead of time, so if it's totally unreasonable, I'm sorry. But you do this conversion, and this is the part students don't like. I had a student during one of my visits say, am I going to have to convert? And I'm like, I'm sorry, yes, because it just happens. So we would say 10 pi revolutions per minute, and that's the pedal. That's the A. That's 10 pi revolutions per minute. Radians per minute. Often you would know the radius of that as well. You could go measure it. So let's pretend the radius of my gear that I'm pedaling is 3 inches. I don't know if that's reasonable. Let's say 4 inches. Actually, let's make our life easier. Make it 5 inches. I should really have planned this ahead of time. Okay, you can now get V. It's just a little dance of this formula. You multiply those two things, so this is 50 pi. And then a cool thing is you can connect various things. You can say A and B have to have the same linear speed, because if you were standing on this chain, it's going to be the same speed linearly wherever you are. So then this is 50 pi. And then you say, well, I know the radius of B, I can measure it, and so then I can figure out the omega. And then these two have to have the same angular speed. It's a fun little dance of these values. But there was one thing I wanted to say here, which was the following. When you do this, and this is what I saw some student ask during one of my visits, if this is 5 and this is 10 pi, and I just computed and I said this is 50 pi, what happens if we throw units in there? And this is a very good question that I've seen many students ask. The linear speed is going to be, in this case, inches per minute. And on the other side, you're going to have 10 pi, and this is going to be radians per minute. And you're going to have R, and that's going to be inches. And if you've taken physics or anything, you're expecting things to cancel. And there's this weird extra unit that appears to vanish. We've come to call something like this a dimensionless unit, meaning you can just remove it. It represents something, But this is the part that's the debatable piece. So when you're using this formula, you have to understand, if you're doing dimensional analysis, that radians is a dimensionless unit and it goes away. It's because of this connection. One radius is the same as the length along the edge. So radians is a different sort of unit than other types of units you're sort of used to working with. And it is good you have questions about why it's going away. It's correct. Okay, so now I'm going to show you some of that history of that piece. Let's get rid of Harry for just a second. So I'm just going to use, this is not clever. I'm going to look at the Wikipedia here. I already read through this. So it says that in 1909, we started to use radian or rad for this symbol. It says that these formulas have been used for a long time, but there's famous examples of people saying the current state of affairs inevitably leads inevitably to ghostly appearances and disappearances of the radian in dimensional analysis. So these are famous mathematicians, scientists of the past who asked the same question that I saw students ask 2 weeks ago in high school class. So there's several talks about how this goes. In 1993, the American Association of Physics Teachers specified that the radian should be explicitly appear in certain places and not in other places, which formulas it should be in and which it wouldn't. So you can see people have had to deal with this. It says that dozens of scientists in the last century have proposed that it should be a base element and have dimension in certain situations and shouldn't. So this question is long-standing. So how we handle it, the formula is correct, but how we handle it in terms of dimensions has really bothered physicists for a long time, is what I'm getting. And so if you're a student and you're feeling that, you're not alone. It talks about the measurements, a few other things here, some history. It comes up in various pieces. It's extremely valuable. There's more of the history here. It says here that Euler used this formula all the time. He had to for all the stuff he was doing. And it was commonplace, but he didn't give it a measurement he just used the formula. He didn't use it as a... So before it was, we just called it a circular measure. It wasn't actually a unit. So the question is whether we should even call it a unit at all. It is helpful to have a name for it, I think. So I think I'm in that school of thought. But anyways, an interesting thing I saw was the debate continued. And even recently, it says in 2013, which I thought I saw more recent. In 2021, they could not reach a consensus on dimensionless quantities. It says in 2013, someone gave a presentation of inconsistencies arising from radians. That's 2013, rather than using it as a base unit. So this is not about whether we should get rid of it, but how we should classify radians, a dimensionless unit or as a base unit. That was 2013. It says they've discussed it, and then in 2021, they couldn't come to a consensus. So within the official, there's still debate about what to call radians. So I thought students might be interested in that history. But mostly, this idea of V equals omega R is really useful. And let's send Harry on his merry way as we leave. I hope that was interesting. Sorry, I'm sure I talked for too long. But thanks for listening. I find that quite interesting. Once we have the formula and we agree we have it, we can find sectors and wedges based off of that by thinking in terms of fractions. So I'll follow up in some future video on that, how we actually use this to do motion, how I'm making things like this that you're seeing in front of you. The reason I can do this is because I know radians and can work with circular motion pretty well. But hope you found that interesting. Give me a like or subscribe if you did.